Hello guys, it's Ert here, and today is the 5th episode of Rewriting Physics. Today we will be looking at photometry, so that includes radiant energy and luminous energy. In traditional notation, these are QE and QV, as well as all of the other things that derive from them. And we note that radiant energy has units of joules, and luminous energy has units of lumenseconds. And lumenseconds are sometimes called talbots. This is the unit we'll be using. Usually, to my knowledge, talbots use the symbol of a capital T, which conflicts with the Tesla, but I will be using TB in this series. With that being said, we will start off with creating our new notation, with defining these in our new notation. And this will be lambda tilde. Radiant energy will be lambda tilde. Luminous will be lambda. I'll also note that we have a similar thing to lumenseconds already happening with current and charge, as we have defined our charge, which usually would be ampere seconds in base units instead of just coulombs. We have just carried that over. So there is a little comparison there to be made. And of course, we can also see heat, Q tilde. Usually it's just symbolized by Q, but on this side, heat is also done in units of joules, and we will denote heat as Q tilde. So, with that being said, let's get started with the first couple of topics. That is the radiant energy density, WE, and the luminous energy density, of which I believe was omega in traditional notation. Radiant energy density is just radiant energy, so lambda per volume. So that is very easily done through our diacritics. And luminous energy density is just luminous energy per volume. So we just get lambda per volume. Those are easy to define. Next, I would like to cover radiant flux and luminous flux. Radiant flux, Phe in traditional notation, is just the derivative of the radiant energy. So that would be joules per second. Usually we would go by base units and see that this has units of watts, which are equivalent to power. But because we are referencing this in terms of the luminous energy itself, we will instead note that it is the derivative of the unit we're looking at. So V lambda tilde is our notation for that. And similarly, if we look at luminous flux, we can find a similar thing where we've started with talbots per second as the derivative of the luminous energy. And so we just get V lambda as our new notation for flux. Next, I would like to look at spectral flux, of which there is no luminous counterpart to it, as far as I'm aware. So spectral flux has versions of frequency and wavelength. So frequency and wavelength. So when we look at this, we see that the origin for these is respectively the radiant flux per frequency and the radiant flux per wavelength. Because of the way these are set up, we've got joules per second per 1/seconds, which is just times seconds. So that just cancels out to joules. The way we will denote this, instead of just using lambda itself, we will use epsilon lambda. So there you go. That is the way we will define that. And that needs a tilde over it. And then when dividing by wavelength, we can see that this has units of joules per seconds meters. And this can be seen as a frequency with units of negative lambda. There we go. And next, I would like to look at radiant and spectral intensity. Radiant intensity, if we go down, thank you. Radiant intensity, which is denoted IE omega. Radiant intensity is the flux over the solid angle. So we see it is the flux, which is noted in this way, over the solid angle. And we already have a diacritic for that, and thus we get this. So there we go. And then we can also look at the different versions of spectral intensity, of which again is just the radiant intensity per frequency or per wavelength. These are two different concepts, but similar to the spectral flux, we can see that this will have units of joules per seconds times radiance squared from intensity times seconds. So this cancels out, just leaves joules per radians squared. And so we will denote this as this, where we have the same diacritic as before on intensity. And funnily enough, the next intensity for wavelength, again, is pretty easy to figure out. It will just be a frequency divided by radiance squared of radiant energy. And we can also look at luminous intensity, of which can just be denoted in this manner, as it relates to radiant intensity, as luminous flux relates to radiant flux. Now I would like to look at radiance versus luminance. Radiance is usually denoted by L, so L E omega, and it is just the flux over a solid angle over an area. So we get that it is a flux over a solid angle over an area. And luckily we already have a notation for this, because we can just use diacritics again. And this is what we get. Similarly, when we define spectral radiance, we see that the frequency form of spectral radiance is this, and the wavelength form of spectral radiance is this. Although another notation for this is, now that we've done this, we can just divide by length. And I would like to also show this notation in intensity. So that would be V tilde with this diacritic, and up here with spectral flux, we can look at it in this way: spectral flux per wavelength. Now I would like to show luminance, of which relates to radiance in the same way as radiant and luminous intensity are related to each other. Luminance can just be defined as this, because you'll note that the units are equal there. Now I would like to look at irradiance, which is usually symbolized by an E, and irradiance is just the flux, the radiant flux over an area, and so that is also very easy to define. So that would be this, and that needs a tilde over it. And again, spectral irradiance, so EE frequency and EE through wavelength can just be seen as epsilon lambda with this, and through this diacritic. And again, all we are doing is merging per area and per length into one diacritic. However, again, we can also find the notation as this because of the way the units work. And then I would like to also look at radiosity. And then we note that radiosity is just a different form of irradiance with the same exact units. So radiosity can be just tacked on to irradiance. And then I would like to look at some more items. So we want to look at the radiant exposure, which is symbolized HE. And I just wrote the symbol down for this instead of writing the formula, but this should be accurate. It is just this. Or if we want to be a little bit clearer, we can always just do this. If I can write it, there we go. And now spectral exposure. So those would have frequency and wavelength versions. We recognize that this is just lambda per time, well, lambda per frequency, so I'm just going to write frequency. This is lambda per wavelength, and we can see that these units will end up multiplying lambda by seconds, or we'll end up multiplying luminous energy by seconds. So we can employ the diacritic that we created last episode, well, one of the three, and recognize this as V breathe. And of course, you do sadly need the area. So I will actually write it like this. And of course, that has units based on radiant energy. And then we can also look at wavelength, of which is pretty easy to figure out. That is just per area per length. There we go. Or of course, you can always go epsilon lambda tilde per area per length. That works out pretty well. And then we can also look at luminous exposure. So luminous exposure is the antiderivative of the luminous flux by time. And so we can always just symbolize that using epsilon lambda. And you can see the comparison here. We can also look at the luminous efficacy, which is usually denoted by K. And it is just the luminous flux over the radiant flux. And we will see the units for this would be, oh, not kilograms, would be talbots over, no, be talbots per second over, that is a very fat bar, we'll just go along with that, over kilograms times meters squared per seconds cubed. And we see that the seconds cancels one of these out to give a 2. And so we just get talbots seconds squared over kilograms meters squared. And if we take all the meters out, we will get kilograms times talbots squared on the bottom and seconds squared on the top times meters per talbot, well, talbot per meter squared. And that should not be a square on the bottom, that should just be a 1. There we go. And if we evaluate that, we will get force of 2 lambda. Well, 1 over force of 2 lambda. So we need the bar. But that is the representation of efficacy. And then after that, I would just like to look at luminous efficiency, of which can just be represented as N lambda. And if we are dividing efficacies by each other, we will just want to do, not what I just did, but we will want to do this. There is our representation of efficiency, and here is the representation of efficacy. And I am hoping I got the units right. Anyways, back to the outro. And so, with that being said, we have reached the end of the video. But, with that being said, this has been Ert, and goodbye for now, and peace.